Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry Paper 3. In Unit 2, we are studying about polynuclear hydrocarbons. In Lecture 2, we will be looking at naphthalene and its derivatives Part 2. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayamprabha, MHRD, New Delhi. Let us look at the topics that will be covered in this session. We will be starting our lecture by the electrophilic aromatic substitution reaction. So, how the naphthalene undergoes electrophilic aromatic substitution, which position the reaction actually occurs, what is the basis behind the reaction occurring at a particular positions, all those things we will be studying. We will study about the Friedel-Crafts reactions of naphthalene. Then we will study about some of the examples of electrophilic aromatic substitution, which is the halogenation reaction, nitration reaction, sulfonation reactions, all those things we will study. Then later on we will study about various naphthalene derivatives. Our main focus will be on the amino, hydroxy and the carboxylic acid derivatives of naphthalene, how these compounds can be formed and what are the various reactions of these these derivatives we will be looking in this particular session. Let us move on to the next one, which is the electrophilic aromatic substitution of naphthalene. The electrophilic aromatic substitution of naphthalene is an interesting reaction. Here, the reaction mainly occurs at position number 1. The electrophilic aromatic substitution of naphthalene mainly happens at position number 1 more than at position number 2. In other words, position 1 is much more susceptible to attack by the electrophile than position number 2. We are now going to see what is the reason behind that selectivity in this particular reaction. So, we have earlier seen the difference in energy of activation at various positions. When we look at the naphthalene structure, we have seen this particular structure earlier also. So, there is a difference or a higher bond order at between position 1 and 2. So, here we have 2/3 of the time the bond is having the double bond character of all the resonance structures, and this bond, if you look at this is position between 2 and 3, we have 1/3 of the time the bond is having the double bond character. So, in other words, what we can say is the pi electron density available between the position number 1 and 2 is higher compared to the pi electron density available at between position 2 and 3. So, when there is more pi electron density, that actually leads to lower bond localization energy. We will look at what is the relationship between the bond localization energy and energy of activation for the intermediates. Okay, so these two things we will look a little later. Now let us look at why this particular position, that is position number 1, undergoes reaction much readily, especially the electrophilic aromatic substitution compared to position number 2. So, here one clue between position number 1, 2 and 3 is, of course, position 3 has less pi electron density. So, that means 1/3 of the time only this is having the pi electrons between bond 2 and 3. So, that means position 3 is actually going to be much lesser. We can compare that. And if we look at position number 1, that the bond between 1 and 2 have a higher pi electron density, that is 2/3 of the time they have the higher pi electron density. Of course, when we look at other substituents, then only we will say these 3 and 4 positions are little different, but we have earlier seen the symmetry of this molecule. So, the attack at position 1 and actually attack at position number 4, these are more or less the same site attack only. So, whatever is applicable at position number 1, we can also say that will happen at position number 4. So, when there is a lower bond localization energy, that leads to higher reactivity at that particular position. Let us take some example directly. Let us say we are going to make a electrophile attack on naphthalene. So we have position number 1 and 2. For simplicity, we are only going to compare between position 1 and 2. So the electrophile can attack the position number 1. So this is one site of attack, and we have another attack. We have another attack that is possible at position number 2. So we have two sites of attack. The electrophile can attack at any one of the place. Let us look at if the electrophile attacks at position number 1. So when the electrophile attacks at position number 1, we have this particular intermediate that is formed. So the electrophile attacks this position. So the double bond is now shifted towards this particular carbon. So that's why this position becomes more nucleophilic in nature, so the electrophile can easily attack. So when the bond is polarized towards position number 1, the 2 position gets a positive charge. So this is the carbocation that will be formed after the electrophile attacks position number 1. So when we have a positive charge or a carbocation that is formed at position number 2, then there is a pi bond available here which will donate its pi electron to this particular electron deficient carbon, and this position now becomes the carbocation. So this is how the overall attack at C1 position leads to the intermediate. Okay. If you look at the position of attack at position number 2, so when the electrophile attacks at C2 carbon, what happens is this particular bond. So when we have this bond, so let me say this is how the bond polarization takes place for the C1 attack, and the same bond is polarized towards this carbon when the electrophile has to attack at position number 2. So that means the pi bond can be polarized towards position number 1 or 2. So when the electrophile has to attack at position number 2, then this position has to have the negative charge. So that means the pi electron has to polarize towards the number 2 carbon. So when that happens, there is an electron deficient carbon on position number 1. So when there is an electron deficient carbon at position number 1, then the aromatic pi system, so this is the aromatic pi system. So this pi electron is now shifted towards this particular carbon to stabilize this carbon, which leads to the formation of a carbocation at the ring junction. So if we recall what we have discussed so far, if the electrophile attacks at position number 1, then that particular carbocation, that is the carbocation at position number 2, can be stabilized by the adjacent double bond. So this adjacent double bond is shifted to the neighboring position, so that carbocation is formed here at this position. So this is what happens when the electrophile attacks at C1 position. Now this pi electron system from the aromatic 6 pi electron system is not disturbed when the electrophile attacks C1 position. But on the other hand, when the C2 attack actually happens, that we have seen, the carbocation actually formed here at the position number 1 requires the 6 pi electrons from the aromatic system to stabilize it. So this one of the pi electron is stabilizing this particular carbocation. So which is actually a high energy demanding process, and that is the reason if you look at the carbocation stability, the carbocation formed by the C1 attack is more stable compared to the carbocation formed at the C2 attack. So that is the reason we can actually see why the C1 attack, that is the position 1 attack, takes place when the electrophile adds to the naphthalene molecule. And we also have other examples. Say for example, when we take the case of 2-naphthal, the 2-naphthal can be attacked at the position number 1 as well as at position number 3. So these are all the two places as shown here, 1, 2, 3, between these three positions, the position number 1 and the position number 3 both can be attacked by the electrophile in the 2-naphthal system. So here if we extend the same thing from the naphthalene, so this particular bond, the 1,2 bond has a 2/3 of the time it is having the double bond character, and this 2,3 bond is having 1/3 of the time double bond character. So in other words, if the hydroxy group, that is the naphthal's phenolic hydroxyl, is present at a 2 position, then this particular bond is having more pi electron density compared to the 2,3 bond. So what we can say is that 1,2 bond has more bond localization or more pi electron density compared to 2,3 bond. So what will happen when there is a higher or the greater pi electron density? That leads to lower bond localization energy. When there is a lower bond localization energy, that actually leads to the formation of transition state very readily. That means the sigma bond can be formed very readily because there is more pi electron or the electron density is higher, which leads to the easy formation of the transition state. So what we can say is the energy of activation for this particular intermediate A to form is much lower compared to the energy of activation for the intermediate B to form. So here the attack takes place at one position. So here the bromonium ion is the one which is added, and in this case also the bromonium ion is added to position number 3. So between position 1 and position 3, this particular intermediate A is having lower bond localization energy. That is the reason that is also having a lower transition state. That means the energy of activation is much lower, so that is easily formed compared to the if the halogen atom, that is the bromonium ion, attacks position number 3. Let us move on to the next one. That means what are the different type of substitutions that are possible. So the first one is we talked about the position number 1. So when electrophilic aromatic substitution takes place, generally we end up with the one derivative as the major product. So this is can be explained by the previous one what we have discussed so far. But there are a couple of reactions. Let us look at sulfonation at high temperatures or Friedel-Crafts reactions which are carried out on naphthalene. Here we generally end up with the two substituted derivatives. So these are all the only two reactions which are exception to the normal substitution reactions of naphthalene. So sulfonation at high temperatures and Friedel-Crafts reaction leads to two substituted derivatives of naphthalene. All other reactions of electrophilic aromatic substitutions of naphthalene gives the one derivative. The one substitution actually takes place. Of course, we have two aromatic rings, and when we have two aromatic rings, we can actually expect additional reaction also. Like if we have a monosubstituted naphthalene which undergoes further reactions, then where the reaction will occur, because we have one substitution on one ring. So when the second substitution is added to this compound, where will it go? Will it go to the same ring? That is what is called the homonuclear substitution, or will it go to a different ring? So let us look at the first case, which is a homonuclear substitution. So if the groups which are basically orthopara directing, chlorine, bromine, hydroxy, methyl, NHR or NHAC, like these kind of orthopara directing groups are present in position number 1, and if we carry out the second electrophilic aromatic substitution reaction, we end up with the product which is a homonuclear product. That means the second group which is entering second time, that is the Y group, actually goes in the same ring where the X is actually existing. So and again which position if it goes, in most of the cases if X is in position number 1, the Y will actually occupy the position number 4. So this is very similar to para directing. So we can assume that if we are assuming this is only one ring, so position 1 and 4 are basically para disubstitution. So here in this particular case, the homonuclear substitution leads to 1,4 disubstitution. And if the X group is in position number 2, that means if you are starting with the 2 derivatives as the starting material for the second substitution, then the introducing group or the Y generally goes to position number 1 only. So here we don't it doesn't go to position number 2 or 3 or 4, it always goes to position number 1 only. Say for example, if you have a substitute orthoparadirecting groups, bromine, hydroxy, methyl, or these groups, when they are present in position number 2, the second incoming group, that is the electrophile, goes to position number 1 only. So these are all the, in this case also it is a homonuclear derivative. So if we have orthoparadirecting groups, they generally give homonuclear derivatives on second substitution. And on the other hand, if we have the other groups, say for example, if we have a nitro group or a sulfonic acid group, they generally prefer a heteronuclear substitution. That means if the substitution is on position number 1 or 2, it doesn't matter whether it is in position number 1 or 2. If we have the nitro group or the sulfonic acid group, the second heteronuclear substitution generally happens at position number 5 or 8. So if we start from number 1, this is 1, 2, 3, 4, 5. So the substitution may happen at this position or 6, 7 and 8. So this is second introduction. So the second group may go to the heteronuclear substitution. That means if we have the X group as nitro or sulfonic acid, the second group is introduced in the second ring. Why this happens? Because nitro group is a deactivating group. So that's the reason the substitution does not take place in this particular ring. The substitution takes place in the other ring. And of course, if the X is a halogen or amino group, when it is present in position number 2, at that time also the heteronuclear substitution takes place. So these are the ways by which we can understand, depending on what is the group which is present, we can actually tell where the substituent is going to go. Say for example, if you look at the halogen, if the halogen is in position number 1, so if you look at this one, so here we generally end up with the homonuclear substitution. But if the halogen is in the second position, that many times prefers the heteronuclear substitution. So this is how we can understand, depending on what is the first group that is present in the naphthalene derivatives, the second or the incoming group occupies whether the same ring or the neighboring ring can be understood using this particular scheme. So the next one is the Friedel-Crafts reaction. So as we have mentioned earlier, Friedel-Crafts reaction generally prefers or gives the 2 substitution as the major product. So if we have the R group as the methyl group, both 1 and 2 are formed. That means this 1 substitution is formed as well as 2 substitution is formed. Because this 1 substitution is formed to a lesser extent, the 2 substitution is formed to the major extent if R is equal to methyl group. And if R is an ethyl group, then what happens is there is no 1 substitution, we get the 2 substitution as the major product. So that's what we have seen earlier also. The Friedel-Crafts reaction generally leads to the 2 substitution product in the naphthalene system. And if it is a N-propyl group, there is no 1 substitution product, we only end up with the 2 substitution product. But if you look at the structure, we are starting with the N-propyl halide and the final product formed is actually a isopropyl derivative. In other words, what we can say is there is a carbocation that is involved in this reaction which underwent rearrangement to give the corresponding isopropyl derivative. Because if you look at here, this is what is going to be the carbocation that will be formed from the corresponding propyl derivative. This undergoes rearrangement to the corresponding isopropyl derivative secondary carbocation. So this carbocation actually adds to the corresponding naphthalene system to give the 2 substituted product. So this is one of the ways by which we can actually say which position undergoes reaction in the electrophilic substitution reaction. So if you look at the acylation reaction, that is Friedel-Crafts acylation reaction, acetyl chloride gives actually 1 and 2 derivatives. If it is a carbon disulfide is used as the solvent, the acetylation generally takes place 3:1 ratio for 1 and 2 substitution. But if you use nitrobenzene as the solvent, then the 2 substituted acyl derivative is formed in large excess compared to 1 substituted acyl derivative. So the next one is the chloromethylation reaction. So here the reaction of naphthalene with formaldehyde and HCl leads to the corresponding chloromethylated derivative as shown here. Here again the reaction occurs at position number 1 only. If we look at simple halogenation of naphthalene, we have seen earlier the dry chlorine gas when we are using that actually leads to di and tetra substituted derivatives, but simple halogen atom generally when reacted with the naphthalene produces mono derivatives. And the second halogenation occurs on the same ring, that is the homonuclear disubstitution actually happens. So we end up with the 1,4 disubstituted halogen derivatives. And if we start with this is for the 1 substituted product, because we are talking about here the 1 substituted product. 1 halo derivative can be prepared by this method. If we want to prepare the 2 halo derivative, so how do we make the 2 halo derivative? We start with the 2 amino derivatives. So when we start with the 2 amino derivative, diazotization using NaNO2 leads to the corresponding diazonium salt, and this salt when treated with copper chloride and HCl leads to the 2-chloro derivative as our final product. So depending on whether we want to make the 1-chloro derivative or 2-chloro derivative, we can choose the appropriate starting material. Then the next one is the nitronaphthalene. So when we talk about nitration reaction, the room temperature nitration of naphthalene leads to 1 substituted product, and this 1 substituted product on treatment with the PCl5 leads to the corresponding 1-chloro derivative. So this is another method of preparing halonaphthalenes. And if you use a little bit strong conditions, then the nitration leads to different products. We have the 1,5 and 1,8 dinitro derivatives are formed. So depending on the condition, we can actually get mononitro or dinitro derivatives. And if we want to make a 2-nitro substituted product, then we have to start with the corresponding diazonium salt. So this diazonium salt can be prepared from the amino compound. So once the amino compound is converted to the corresponding diazonium salt, treatment with the sodium nitrate and the copper leads to the 2-nitro derivative. So depending on which position we want the nitro group introduced, we have to choose the appropriate starting material. And if you look at the sulfonation reaction, this is a very important reaction for naphthalene. So depending on the reaction temperature, we can actually get different type of product. That means whether we end up with a 1 substituted product or 2 substituted product depends on the temperature at which the reaction is carried out. If we do the reaction at low temperature like 40 degrees centigrade, we end up with the 1 substitution product, and if we run the same reaction at a high temperature, that is 160 degree, we end up with the 2 substitution product. Now we will see that's why here this is basically called as a kinetic and thermodynamic control of the reaction. So at low temperature, it is basically the kinetic control is happening. So that's the reason we end up with the easily the 1 substituted sulfonated derivative is formed very easily, because the energy of activation for this particular reaction is lower. So that's the reason we end up with the kinetic product. And if we have a high temperature, that leads to stability of the product. In other words, the thermodynamically more stable product will be formed, and that is the reason the 2 substituted sulfonic acid derivative is formed at high temperatures. And of course, depending on whether we have the 1 or 2 sulfonic acid derivatives, we can convert them to the corresponding chloro derivative by treatment with the PCl5. and oxidation by acidic permanganate actually gives the phthalic acid as the product. That means the aromatic ring in which the sulfonic acid group is present, that undergoes oxidation. And if we look at the 2-naphthalene sulfonic acid, this is actually the starting point for most of the 2 substituted derivatives of naphthalene. Various 2 substituted naphthalenes can be prepared starting from 2-naphthalene sulfonic acid. So that's the reason this is the most important compound that is used in naphthalene chemistry. So now we are going to look at naphthalene derivatives. So the first one is naphthalamine. So the naphthalamine can be prepared from various starting materials. The first one we are going to look at is from the nitro derivative. So the 1-nitro-naphthalene on treatment with iron and HCl gives the corresponding amino derivative. And we can also convert the corresponding naphthol. So when the naphthol is treated with ammonia and zinc chloride at a high temperature around 250 degrees centigrade, we end up with the corresponding amino derivatives. Similarly, the carboxylic acid, that is the naphthalene carboxylic acid, 1-naphthalene carboxylic acid can also be converted to the corresponding amino derivative by treatment with hydroxylamine in the presence of polyphosphoric acid. So these are all the different ways by which 1-amino naphthalene can be prepared. And if you look at the reactions of 1-naphthalamine, this 1-naphthalamine reduces the ammonical silver nitrate solution, and it gives a blue precipitate when treated with FeCl3. So these are some of the reactions of 1-naphthalamine. And oxidation of naphthalene, 1-amino naphthalene with chromic acid, that is boiling chromic acid, gives the beta naphthaquinone. So this is where we have given, this is beta naphthaquinone. So this compound is obtained after oxidation of the 1-amino naphthalene compound. And if you use permanganate, that is a much stronger oxidizing agent, that leads to phthalic acid formation. So this particular amino ring, this reaction we have also seen about when we studied about the structural elucidation of naphthalene. The presence of amino group actually activates this particular aromatic ring for easy oxidation. So the activation leads to the breakage of this particular bond on oxidation, leads to the corresponding phthalic acid derivatives. And when we do the hydrogenation reactions of amino naphthalene, the second ring is actually undergoes reduction. So when the hydrogenation is carried out with sodium and isopentanol, we end up with the 5,6,7,8 tetrahydro 1-amino naphthalene is formed. And if we look at 2-naphthalamine, we have a Buchrod reactions which is used for the preparation of 2 amino derivatives. So this is starting from the naphthol. The naphthol is treated with a corresponding aqueous sulfite or hydrogen sulfite solution. We end up with the corresponding sulfonated derivative. That sulfonated derivative reacts with ammonia to give the corresponding amino sulfonate derivative. So here the hydroxy group is replaced by the amino group. So that's why we end up with the amino sulfonate derivative, and this amino sulfonate derivative reacts with ammonia, and this corresponding sulfonation, basically the desulfonation of this particular compound takes place. That leads to the formation of the corresponding 2-amino naphthalene along with the formation of sodium ammonium sulfite. So the same reaction can also be effected with aqueous ammonium hydrogen sulfite at 150 degree under pressure. That also converts 2-naphthol into 2-naphthalamine. So the reactions of 1 or 2 naphthalene sulfonic acid with sodium hydroxide at a high temperature gives the corresponding naphthol. So the equation is given here, sulfonic acid sodium sulfur. If you remember earlier also we talked about the naphthalene sulfonic acid is the starting point for preparing various derivatives. So the 2-naphthalene sulfonic acid is the starting material here for even the preparation of 2-naphthol. And if we treat the 1-naphthalamine with dilute sulfuric acid at very high temperature under pressure, that leads to the formation of the corresponding hydroxide derivative, that is the 1-naphthol is formed. And if we look at specific preparation of 1-naphthol, 1-naphthal can be prepared by the reaction of orthobromofluorobenzene. So, we have the orthobromofluorobenzene. This when treated with lithium gives a benzene. So, this benzene reacts with furan. So, this reaction is nothing but a Diels-Alder reaction. So, the reaction between benzene and the furan leads to the Diels-Alder adduct, and this Diels-Alder adduct on treatment with HCl opens up this particular ring to give the corresponding naphthol. So, here we end up with the 1-naphthal. If we look at the properties of 1-naphthal, the 1-naphthal reduces the ammonical silver nitrate solution. This gives a violet blue precipitate with ferric chloride, and on oxidation with the chromic acid it gives the alpha naphthaquinone. The structure of alpha naphthaquinone is given here. So, here is the position, that is at the 1 position we had the hydroxyl, and which undergoes oxidation to give the 1,4-diketo derivative, that is the alpha naphthaquinone is formed. And when treatment with permanganate, it gives the phthalonic acid. So, the corresponding keto group is introduced in this particular compound. In phthalic acid, we only have the dicarboxylic acid. So, the dicarboxylic acid with 1 carbonyl unit introduced is called the phthalonic acid. So, this is formed on oxidation with potassium permanganate. And when we carry out the reduction of the naphthol, that is hydrogenation of naphthol, we end up with a 5,6,7,8 tetrahydronaphthal. So, here again the ring where the substitution is not present undergoes reduction. And if you look at the sulfonation reaction, the sulfonation of 1-naphthal gives various products. So, if we simply sulfonate 1-naphthal under dilute conditions, the direct sulfonation leads to, here is the 2 substitution, here is the 4 substitution. So, we end up with the 2 product, that is the 2 sulfonic acid, 1-naphthal 2 sulfonic acid, which is called as the Schaffer's acid, or the 1-naphthal 4 sulfonic acid, which is Neville-Winters acid. So, these are all the 2 products that is formed by the direct sulfonation of naphthal. Under vigorous conditions, we end up with the polysulfonic acid substituted derivatives. So, the 1-naphthal gives 2,4-disulfonic acid and 2,4,7-trisulfonic acid are formed. So, here we have the 2 and 4-disulfonic acid, and we have 2, 4 and 7 trisulfonic acid derivatives are formed on vigorous sulfonation reaction. And when we treat naphthol with nitrous acid, we end up with 2 types of product. One is the 2-oxime of beta naphthaquinone, that is A as shown here, and we also end up with the 4-oxime of alpha naphthaquinone. So, these are all the 2 derivatives, 2 oxime derivatives that are formed when naphthol is treated with nitrous acid. And similar to the normal coupling reactions, 1-naphthal undergoes coupling with the diazonium salt at position number 4. So, we end up with the azo compound as shown here. So, here is the 4 position, that is at the para position of the hydroxy group, the condensation takes place. The azo compound is formed at 4 position. And when we talk about the 2-naphthal, this is also very similar to 1-naphthal. This reduces the ammonical silver nitrate solution. This gives a green precipitate when treated with ferric chloride. Oxidation also gives the same phthalonic acid, and hydrogenation using sodium and isopentanol again gives the similar derivative. So, in the 1-naphthal we have the 5,6,7,8 tetrahydro 1-naphthal derivative, and when we start with the 2-naphthal, we end up with the 5,6,7,8 tetrahydro 2-naphthal. So, in both the cases, the ring where the substitution is not the alcohol, the hydroxy group is not present undergoes hydrogenation. And when we look at reactions with the nitrous acid, here we end up with only 1 product. That means we get 1 oxime of beta naphthaquinone is the only product that is formed when 2-naphthal is treated with nitrous acid. And when the 2-naphthal couples with the diazonium salt, we end up with the condensation, or the azo group is introduced at position number 1. For 1-naphthal we get 4 substitution. For the 2-naphthal we get the substitution at 1 position. And if you look at the sulfonation of naphthal, similar to 1-naphthal, this also gives various substituted naphthal sulfonic acids. Especially the direct sulfonation gives actually the 2-naphthal 1 sulfonic acid, which is quite unstable, and this rearranges to, this is the 8th substitution. So, this position is the 8th position. So, 8 substituted 2-naphthal is formed, and this at high temperature rearranges to give the 6th substituted product. So, the 2-naphthal 6 sulfonic acid is formed. This is by the direct sulfonation reaction, and if we use highly concentrated sulfuric acid for the sulfonation reaction, we get 2-naphthal 6,8 disulfonic acid. That means this is the 8th position, this is the 6th position. So, the 6,8 disubstituted sulfonic acid is formed as the major product, and we also have the 3 and 6 disubstituted product is formed as the minor product. So, these are all the various sulfonation reactions of 2-naphthal. And if we do a comparison of the reactions between 1-naphthal and 2-naphthal, both 1-naphthal and 2-naphthal reduces ammonical silver nitrate, but they give different type of products. For example, 1-naphthal gives a violet blue product precipitate, whereas 2-naphthal gives a green precipitate when treated with ferric chloride. Chromic acid oxidizes 1-naphthal to alpha naphthaquinone. Both permanganate converts 1-naphthal and 2-naphthal to thalonic acid. Sodium and isopropanol hydrogenation leads to 5,6,7,8 tetrahydro derivative. Depending on whether it is 1-naphthal or 2-naphthal, the hydroxy group is present at that corresponding position. And when we use sulfuric acid for sulfonation, that is a direct sulfonation, we end up with a 2 and 4 sulfonation for 1-naphthal, whereas 1 sulfonation happens for 2-naphthal. And if you use harsh conditions or a very concentrated sulfuric acid for the sulfonation, we end up with a polysulfonation. The positions of the sulfonation actually differs between 1-naphthal and 2-naphthal. Nitrous acid gives the corresponding oximes. So, the 2 oximes of beta naphthaquinone and 4 oximes of alpha naphthaquinone are formed when 1-naphthal reacts with the nitrous acid. The 1 oxime of beta naphthaquinone is formed when 2-naphthal reacts with nitrous acid. And in the case of diazonium salt, for the 1-naphthal, generally the reaction occurs at the 4th position, and for 2-naphthal it occurs at position number 1. So, this is the difference between the diazonium coupling between naphthal and benzene or similar diazonium salts. Let us look at naphthalene carboxylic acid. The hydrolysis of 1 or 2 cyanonaphthalene generally gives a corresponding carboxylic acid, and the oxidation of 1 or 2 acetyl naphthalene by sodium hypochlorite also gives a corresponding acids. So, these are all the simple and the direct method of preparing corresponding naphthalene carboxylic acid. And the reaction of 1-naphthyl magnesium bromide with the acetic and acid anhydride, especially here the acetic anhydride gives the corresponding ester, and the ester can be hydrolyzed to get the corresponding carboxylic acid. So, if we start with 1 naphthyl magnesium bromide, we end up with the 1 naphthalene carboxylic acid. So, depending on the position, we can get the corresponding naphthalene carboxylic acid product. When we look at the next compound, which is the naphthaquinone. So, the 1,4-naphthaquinone may be prepared by the oxidation of corresponding diamino dihydroxy or amino hydroxy naphthalene. So, if it is diamino, the X and Y are both amino groups, that on oxidation gives the naphthaquinone, or we can also use dihydroxy derivatives, or one of them is amino, another one is hydroxy. Like that, various starting materials on oxidation with potassium dichromate and sulfuric acid gives a naphthaquinone, that is alpha naphthaquinone. Even naphthalene on oxidation using potassium dichromate and sulfuric acid gives the alpha naphthaquinone. The only difference is the direct oxidation of naphthalene gives only 40% of the alpha naphthaquinone, whereas the substituted amino or the hydroxy naphthalenes give a better yield. Like here in this case we have around 70 to 75% of the alpha naphthaquinone. This compound is reduced by zinc and HCl to the corresponding dihydroxy compound. Oxidation gives the breakage of this particular bond. We end up with a phthalic acid. And 1,2-naphthaquinone may be prepared by the oxidation of 1-amino-2-naphthal by dichromate or sulfuric acid. So here we have the 1,2. The previous one what we saw is the alpha naphthaquinone, which is 1,4-naphthaquinone. Here it is 1,2. And this is called the beta naphthaquinone, and this is formed from the corresponding 1,2-amino hydroxide derivative, and this on treatment with HOCl leads to the hypochlorous acid, gives the corresponding oxidized product, that is the 2 hydroxy groups are actually introduced into the product, and this can be opened up to give the dicarboxylic acid, which loses water molecule to give the cyclized product. So in this particular case what actually happens is one of the carboxylic acid, that is the green color one what we have shown, is actually moving towards this side, and this hydroxy actually forms the ester. So the hydroxyl and the acid forms the ester formation. That is how we get the lactone as shown here, and this hydroxy remains as it is, and the carboxylic acid group is formed at here. So this leads to the formation of the corresponding phenylglyceric orthocarboxylic lactone is formed in this particular reaction. Let us recap what we have studied so far. We have studied about the electrophilic aromatic substitution of naphthalene. So how the reaction specifically takes place at position 1 compared to position 2, we have actually seen what is the transition state energy of activation and the stability of the carbocation, and how these decide what is going to be the substitution position we have seen. We have also studied about what is Friedel-Crafts reactions of naphthalene, halogenation reaction, sulfonation and nitration reactions of naphthalene. We have seen how the 1 substituted and 2 substituted derivatives can be prepared. All those things we have seen. We also have studied about the various naphthalene derivatives, especially the 1-amino and 2-amino derivatives, 1-hydroxy, that is 1-naphthal and 2-naphthal, and we also studied about the corresponding carboxylic acid derivatives, that is 1-naphthalene carboxylic acid and 2-naphthalene carboxylic acid. How these compounds are formed, what are the different reactions of this compound, all those things we have studied. With that, we conclude this session. Thank you.